welcome to a new video by Access Academy. My name is Johan and I will be your host in this video. So today we're going to dive into QuickSort, one of the most popular and efficient sorting algorithms used in computer science. So if you have been following along, we just covered the merge sort, another divide and conquer algorithm. QuickSort is a little bit similar in its approach, but it uses a different strategy for sorting the data. QuickSort is highly efficient and it uses the divide and conquer approach just like merge sort. But unlike merge sort, which divides the array in two equal parts, QuickSort picks a pivot element and partitions the array around the pivot. The goal is to position the pivot such that all elements smaller than the pivot come before it and all elements greater come after it. So that means we take the array, then we take a random number, that's the pivot, and everything that is smaller gets put on the left side, and everything that's greater than the pivot is getting put on the right side. So imagine you're organizing a bookshelf. You pick a random book as a pivot, and then you place all the books smaller than the pivot on the left side, and all the books that are larger you put on the right side. You repeat this process for the left and the right sections until the entire shelf is sorted and you don't have any books anymore. So let's first create an array. So we can say var numbers. For the people who are wondering why I'm using numbers in all my videos, numbers are the easiest way to teach you this. If you want to do this with something else like strings and anything, that works as well, but you have to change the functions a little bit. But in this case, we're just going to use numbers because it's easy to work with. Okay, so we can say 10, 7, we can say 8, 9, 1, and 5. Under here, we can create our first function. And let me think really quick. So I think it's easier if we create the partition function first. So let's do this nice in order. So we can say func partition. And we're going to take underscore of r. And we can call inout. And we're going to take an array of int, comma. After that, we're going to take low. So low is an int. And we're also going to take high. And high is also an integer. And we're not going to return anything. Okay? Inside here, we can say let pivot is equal to r. And we're going to take the index of high. Then we can say var I is equal to low. Is equal to low. And now under here we can say for j in low dot greater than high. Let's open this up. We can say if r of index is going to be j is greater or equal to the pivot. Let's open this up again. We can say r dot swap at, and we're going to say I, and we're going to call j. And after that, we can say y plus equals 1. We're going to escape the for loop. And under here, we can say r dot swap at. And we're going to say I. And for j, we're going to say hi. And after that, we're going to say return y. Just like this. So now we're going to create the next function. And that's going to be QuickSort. So above here, you can say var quick. What's this? Unexpected non-void return. Oh yeah, I already see the problem. We need to return an I. So we can say return, and we're going to return integer. So now for the QuickSort, we can say func quick sort. We're going to say underscore r, and this is going to be inout. And we'll have an array of integers. After that, we call low. So low is going to be int. High is also going to be int. And we're not going to give this a return function. We're not going to give this a return value. So now we can say if low is greater than high. Let's space this out. As I said before, code completion sometimes is a disaster in playgrounds. So in here we can say let pivot index is equal to partition, and we're going to partition r just like this. And for low, we're going to take low. And for high, we're going to take high. And this has to be high, not height, just like this. Perfect. So after that, inside here, we can say QuickSort. We're going to take R. And for this, we can say low. And high is going to be the pivot index minus 1. And we can call one more time. So QuickSort. We're going to call R. And then we have the low is going to be pivot index plus 1. And high is going to be high, just like this. So let's break this down really quick. So the QuickSort function calls itself recursively to sort the subarrays. The partition function rearranges the elements around the pivot and returns the pivot's final position. We then apply QuickSort again to the left, that's this one, and to the right subarrays around the pivot until the entire array is sorted. So let's run this. So let's see what happens when we say print numbers. So let's also call the QuickSort. Let me see really quick. We're going to call QuickSort numbers, and low is going to be 0. And for high, we can say numbers dot count minus 1, just like this. So let's run this and let's see what happens. Boom, finished. So 1, 5, 7, 8, 9, 10. So what is happening, to explain this guy, there's an easy layman terms. So they take a pivot, and I expect that the pivot is the 7, so that's the middle. And what is happening? So they take the 7, then the sorting algorithm, so that's this one, the QuickSort first and the QuickSort second. So if it's smaller than 1, or if it's 1 smaller than the pivot, so the pivot, that is the value that we take here. And if it's smaller, we put it on the left side. But if it's higher, so if the pivot index, or if the number is higher than pivot index plus 1, it's going to be put on the right side. And as you can see, this is a little bit easier than merge sort. It's less code as well. And yeah, it works very well. QuickSort is particularly effective for large data sets, and its in-place sorting makes it suitable for scenarios where memory space is limited. So QuickSort is also the basis for many order sorting algorithms and is often used in libraries and frameworks. So what does this mean when memory space is limited? So I think we never talked about memory management on this channel, did we? I will make a video about that in the future somewhere. So when you are storing a value, right? So variable or constant. So you have to see this little box. So the little box is put into a shelf, and the shelf is your memory. And the more stuff that we put inside the box, so for example, an array with 1,000 variables, for example, I just say something for that 1,000 values, the box gets bigger because it uses more memory. And because QuickSort uses in-place sorting, it doesn't sort the entire array into memory at once, but it starts to add new values while it goes, right? So everything that's on the left goes into the left, everything that goes into the right goes into the right. So while the values are working, it uses less memory this way. This is the easiest way how I can explain this, because memory management is really difficult. But we will talk about this in a future video, so don't worry about it too much. But just know, QuickSort is an amazing algorithm. So that's going to be the end for our QuickSort video. QuickSort is powerful and really efficient, and it's widely used in practice. So in our next video, we're going to start exploring something that is called the graph algorithm, and we're going to talk about BFS, so breadth first search. And this is a fundamental technique for traversing graphs. If you have any questions or topics that you want us to cover, leave a comment below or come to the Discord channel, because we are really flexible and we're always happy to create some videos about a certain topic that you are interested in. Okay, so thanks for watching, and I see you next time.